Okay, there are basically three areas in machine learning: supervised supervised learning, unsupervised learning, and reinforcement learning. So in the supervised learning, most of the time you can use it to do classification or regression. It is an area of the machine learning task that you can feed a function that maps an input to an output based on examples input-output pairs. So it infers a function from the labeled training data consisting of a set of training examples, right? As this one showed in the slides, as you can see. So in the supervised learning, each data point is a pair consisting of an input object and a desired output value. A supervised learning algorithm analyzes the training data and produces an inferred function, which can be used for mapping new examples. So an optimal scenario will allow for the algorithm to correctly predict the output for any unseen input. So this requires the learning algorithm to generalize from the training data to unseen situations in a reasonable way. The popular algorithms in this area are, for example, regressions, decision trees, support vector machine, LDA, and k-nearest neighbor, and also multi-layer perception, which is actually neural network. So in the unsupervised learning, so this area, it is a type of machine learning that looks for the patterns in the data set with no pre-existing labels and with a minimum of human supervision. In contrast to supervised learning that usually makes use of human labeled data, but unsupervised learning allows for modeling of probability densities over inputs. So to compare supervised and unsupervised learning here, we have an example shown in this slide. So the classification is the most popular problem in supervised learning. So the similarity the counterpart in unsupervised learning is the clustering problem. So we can compare them here to get a sense of the differences between the supervised learning and unsupervised learning. So in the classification problem, the data, you have the data that is labeled. So you train on this labeled data. While in clustering, you have the data, but the data is not labeled by human beings. And in the classification, you can predict the class name. For example, you can say, okay, this image is dominant by sky, right? And that image, mostly it shows you vegetation. But in the clustering, the output is, so the similar data points are finally grouped together. For example, given an image, the algorithm can tell you which group it belongs. It is similar to this group, or it is similar to that group, or more similar to that group. But the algorithm cannot tell you what does the group mean. So it's just find a similarity. So this is the difference between supervised learning and unsupervised learning. And the algorithm, you have k-means and PCA and autoencoder or and GAN models, which is the generative adversary networks. And then the third area is reinforcement learning. It is a type of machine learning technique that enables an agent to learn in an interactive environment by trial and errors, using feedback from its own action and experiences. So it is a concern with how agents ought to take actions in an environment in order to maximize the reward it can accumulate. So the agent think it as it is actually a part of this whole framework that takes action and receive reward from its previous action and get a new environment state as a result of the previous action. And the environment, it represents the outside world that interacts with the agent. And the action of an agent is, so what it does is, while interacting with the environment, it take an action. This is the meaning of it. And there's a interpreter in this loop. So it is actually a function that releases rewards to the agent based on the response of the environment, and then update the state of the agent. And the state is the condition or a position in which the agent is currently exhibiting or residing. And the rewards is very intuitive. It is an indicator to the agent how good or how bad the action taken was. So though both supervised learning and reinforcement learning are used for mapping between input and output, right? But unlike supervised learning, where the feedback provided to the agent is a correct set of actions for performing a task, the reinforcement learning use rewards and punishments as signals for the positive and negative behavior. And another difference is, so in the supervised learning, you have your training data, but when you look at the reinforcement learning loop, there's no training data. It's actually generating the data itself and train on the generated data. And it is used in decision making and robotics. And the popular algorithms include Q-learning, SARSA, and deep Q networks. So today,
Charles, a quick question from the audience. What would an example reward be in that scenario? How would you formulate a reward?
So the reward, for example, if you want to train a driver that is driving our car on the road, and if you turn to left and you went out of the road, then the interpreter will say, okay, this is bad based on a criterion, right? This is bad and you will get a punishment, not a reward. So it gives you a negative value and send that to an agent. But if you say, if you take an action and you're still on the road, then the reward will be a positive value and it will send to the agent. That's how it works. So it's the function release the reward based on a criteria that you set.
Thank you.
Yeah, okay, cool. So the use of machine learning across many fields in the natural hazard engineering, it actually has a long history and has seen a rise in recent years from data acquisition and recognition for example, modeling, simulation, reconnaissance purposes to predictive surrogate models of observed and simulated data. In recent years, a huge amount of engineering and sociological data have been generated, and they have been cleaned and made accessible to the public. So the accessibility to this data, together with the breakthroughs in computer hardware and development of the advanced analysis algorithm, leads to the accelerated discovery and automation in many areas, which includes natural hazard engineering. For example, hurricane, earthquake, flood, wildfire. So machine learning is also almost everywhere. For example, for hurricane, machine learning is used to predict hurricane wind-induced damage of residential structures. And it also has been widely used in earthquake engineering. For example, seismic wave discrimination and earthquake early state warning. Also, ground motion simulations and post-earthquake damage detection from images. Also, seismic risk analysis of structures can also use machine learning. And deep learning is another topic we will cover later. It is broadly used for regional flood or a wildfire susceptibility analysis of images. Basically, you can simulate a system using a physics-based model. But meanwhile, with machine learning, it can be used to build approximate or surrogate models to statistically predict the performance of a system instead of running a physics-based model. So in natural hazard engineering, the supervised learning is the most widely used method among the three areas. And a big part of it is classification. So in this problem, we want to know what class an observation belongs to. So the ability to precisely classify observation is extremely valuable for various natural hazard engineering applications, like predicting whether a building would collapse during an earthquake, or forecasting the wave height of a storm surge. And the popular algorithm in this family includes these, for example, regression, decision tree, random forest, k-nearest neighbor, support vector machine, and neural network. So we're going to cover this topic later. And the keyword in supervised learning are data model training. So that means you're going to use the data to set the parameters of a model to fit the labels. The first algorithm we're going to talk about is the linear regression. There are actually a lot of regression models, but the linear regression was the first type of regression analysis to be studied rigorously and to be used extensively in practical applications. So in statistics, linear regression is a linear approach to modeling the relationship between a scalar response and one or more explanatory variables. So let's use the simple linear regression as an example here to learn the idea of it. So for example, you are given a few pairs of X and Y, right? Now you are trying to estimate Y given a new X. So here Y is the response variable and X is the explanatory variable, right? So what we can do is trying to find out a relationship between X and Y. And in linear regression, we make an assumption that Y is a linear function of X. So Y equals to X multiply coefficient beta plus an error. And if we plot the data and the regression function together on the right, you can see the blue dots are your data points. And the corresponding outputs predicted by a regression function are the red ones. The difference between the data and the prediction is called residual. The objective is to find the coefficient and the error in the function that can minimize the residual. And we simply plug them into the regression function, and we can always find the value of y given the new x. So in this example, you have only one explanatory variable, which is x. The case is called simple linear regression. The case of more than one explaining variable is called multiple linear regression. That's the idea of linear regression. Then we can talk about the logistic regression. So in the case of a logistic regression, the response variable y is categorical. As you can see in this example, you have only 1 or 0 for y. So what we are trying to do is we are trying to classify the data points into categories. 1 represents one category and 0 is another category. So instead of the linear regression function, in order to find the relationship here between x and y, we need to find another function. This function is called the logistic function. It means the probability of y equals to 1 given the value of x. So when we draw this function in the figure with the data, it looks like this, right? And it gives you a prediction for a given x and its probability. You can then draw a threshold and use the threshold to classify the prediction into different classes. And then you want to find the coefficient beta that can minimize your prediction with the ground truth. So this is the idea of logistic regression. So the decision tree is also pretty intuitive. So I'd be willing to bet that most people have used a decision tree, knowing or not, at some point in their lives. It's probably much easier to understand how a decision tree works through this example. So imagine that our data set looks like this. You can see we have circles and triangles. They represent a building is, the triangle represent the building is not safe. And the circle represent that the building that are safe. And the x, in the x direction, the meaning is the year the building built. And in the y direction, it means the design level, right? So here, x and y are called features of your data. So each data point can be represented by these features. And you can add many dimensions into these features. Here, this simple example has these only 2 features, okay? So how can we use decision tree to classify them? We want to separate the data points based on their features. So we can separate them by asking a series of questions regarding to their features. Here in this example, the features x and y, right? We can ask our first question about one of the features. For example, x. Is it built before 2000, right? Based on this question, we can draw a separator to divide the data into 2 groups. As you can see, the separation is not perfect. You have both circles and triangles in 2 groups. If your answer is yes to the question, you look into the data that meets the criteria, and you can ask another question to further separate it, right? And then you can separate this subset into 2 groups perfectly. And then you go back to its previous node. So you can think of a node in a tree as a point where the path splits into 2. So observations that meet the criteria go down to yes branch, and the ones that don't go down to the no branch, right? So in the no branch, you are going to ask another question about another feature. And if your answer is the yes, it go to the triangles, and no, it go to the circles. So this is the basic idea of decision tree. And for a data, you can build many decision trees. This one is shows we start from X. You can also start from another feature, for example, from Y, right? Then this tree looks like this. And based on decision tree, we can introduce random forest. So it is a method that is built based on decision tree approach. Instead of building only one decision tree that is trained on the whole data set, the random forest, like its name implies, consists of a large number of individual decision trees that operate as an ensemble. Each individual tree in the random forest spits out a class prediction, and the class with the most votes or with the most votes becomes the model's final prediction, or you can also average these votes at the final prediction. So how do we build a random forest? We can divide it into these steps. Firstly, we randomly select a subset of data from the original data set, and we can build a decision tree based on this subset data, right? Then we repeat this process to build many trees. At the end, each tree can give a prediction for a data point. We choose either the majority vote or the averaged prediction at the final result of this random forest model. So this way, the random decision forest correct for a decision tree's habit of overfitting to their training data set. The fundamental concept behind the random forest is a simple but powerful one. It is the wisdom of crowds. The reason that the random forest model works well is because so you have a large number of relatively uncorrelated model, which are the trees, and they are operating as a committee. So the committee will outperform any of the individual constituent models, right? Then we talk about.
May interrupt briefly. We had a question previously, and that was who determines those questions? Us, or is this how the algorithm works? So I'm not completely sure where that fits.
Yeah, you don't have to control this, and the algorithm can help you to choose the questions. Basically, it chooses from a range, and you can control like how many layers in your decision tree, like how deep your decision tree can go, and the algorithm can help you to like choose from this range. Yeah, that's the idea of this algorithm. Because if you know how to choose these answers, that means you already know how to classify your data. Then there's no meaning for you to build a decision tree, right? It's already in your brain, right? So you don't actually know how to choose a question, and it will be asked by the algorithm. Is that clear?
Yes, thank you.
Cool. So this is the k-nearest neighbor algorithm, or KNN. So it's another simple algorithm that stores all available cases and classify new cases based on a similarity measure, which is the Euclidean distance. So the KNN has been used in statistical estimation and pattern recognition for a long time. in this algorithm, a data point is classified by a majority vote of its neighbors. So with the point being assigned to the class most common amongst its k nearest neighbors, measured by a distance function. For example, given a black dot is positioned here, right? And you can find, for example, we want k equals to 4. We want to use 4 nearest neighbor to classify this black dot. You can select the 4 nearest one, and you can find there are 3 circles and only 1 triangle. So you know this black dot belongs to the circle group. That is the idea of the KNN. So if you use k equals to 1, the case is simply assigned with the class of this nearest neighbor, right? You can also increase k to a bigger one, right? Then, but it's not always good for you to increase or decrease k. You will need to find an optimum that best fit your data. Yeah, we will see this in an example, how the k is influencing your performance. So now you have accustomed yourself with linear regression, a logistic regression, tree and forest, also the KNN method. So another one, support vector machine, abbreviated as SVM, is another simple algorithm that every machine learning engineer should have in his or her arsenal. The SVM is highly preferred by many as it produces significant accuracy with less computation power. So SVM can be used for both regression and classification tasks, but is it widely used in classification objectives? So what is a support vector machine or a SVM? So the objective of the support vector machine algorithm is to find a separator in an n-dimensional space that distinctly classify the data points. So n is the number of features of your data point. Let's firstly look at this example with its data points in the 2D space. And the features are x1 and x2. So to separate the 2 classes of data points, there are many possible separators that could be chosen. But which one is the best? So support vector machine will probably say, this is the best. This is the best separator. Because based on this separator, we can find the widest band that splits the data into 2 groups. So the band is called the margin. And the separator in the center of the margin is called the hyperplane. So hyperplanes are decision boundaries that help classify the data points. Data points falling on either side of the hyperplane can be attributed to different classes, right? So also the dimension of the hyperplane depends upon the number of features. So if the number of input features is 2, then the hyperplane is just a line. If the number of the input features is 3, then the hyperplane becomes a 2-dimensional plane. It becomes difficult to imagine when the number of features increase, right? So support vectors are data points that are closer to the hyperplane and influence the position and orientation of the hyperplane. So using these support vectors, we maximize the margin of the classifier. So deleting some support vectors will change the position of your hyperplane. So support vectors are the points that helps us build the SVM, right? So the math here is, its objective is to find a hyperplane that has the maximum margin, which is the maximum distance between data points of different classes. So maximizing the margin distance provides some reinforcement so that future data points can be classified with more confidence. So we're not going to deeper about how to maximize the margin, but it is a constraint optimization problem. Okay, let's go to the next slide. So it looks simple in the previous SVM example. However, not all data are linearly separable, right? In fact, in the world, almost all the data are randomly distributed, which makes it hard to separate different classes linearly, right? As you can see in these examples, it's very hard to find a separator to just split the two groups. So one of the solutions is the kernel trick. The kernel trick is widely used in SVM to bridge linearity and nonlinearity, right? The idea of it is very simple. If we find a way to map the data from the lower dimension space to a higher dimensional space, we will be able to find a decision plan that clearly separate the two groups, right? As you can see in this data transformation process, the 2D point is mapped to a 3D space, right? The mapping from the lower dimension to higher dimension is done by kernel functions here. And the process is called kernelization. So the 2D point is mapped to this 3D space so that you can find the boundary easily and make the classification. And if you visualize the boundary in the original lower dimension space, it looks like this. Right. So there are different kernels you can use. The most popular ones are the RBF and the polynomial kernel. Here's a video that shows the kernel trick. Let's look at the video.
Charles, you need to unmute yourself or we don't have audio.
There's no audio in the video, so it's fine. See, this is a mapping to 3D. And you can cut it by a hyperplane, right? And then you can map it back to the original space. So you have learned these models. We went through this conventional machine learning algorithm, right? You have learned these models. Now you know how this algorithm work. You can choose one algorithm to build for your model, build for your data. But how to tell if the model you build is good or bad, right? So we can draw a confusion matrix to measure how good it is or how bad it is. So a confusion matrix is a matrix that looks like this. So you can see you have true positive, false negative, false positive, true negative. What does it mean? So for example, you have these two classes. One is, so if you answer is yes to the class, then it's positive, right? It's negative is 0. So in your prediction, when your prediction is 1 and it's actually true, that means you get a true positive. If your prediction is 0 and it's true, you get a true negative. And your prediction is 1, but it's actually false, you have a false positive. And the last one, if your prediction is 0, but it's actually false, that means you have a false negative. And then you can use this to calculate the matrix here at the bottom, right? For example, you can calculate a recall. So the recall means how much of the positive class are correctly predicted by your model, right? You want to get the number as high as possible. And the precision it means in all the positive cases we have just predicted, how much are actually positive, right? And then accuracy, it means out of all the cases in the prediction, how much we predicted correctly, right? We want to get this value as high as possible. But which one is best measure to tell you the performance of your model? Better than these ones is the F1 score. So F1 score is the mass here is a harmonic mean of your recall and your precision, because it is difficult to compare two models with low precision and high recall, or vice versa, right? So to make them comparable, the F score is a good metric. It helps to measure the recall and the precision at the same time. So when building these prediction models, the primary goal should be to make a model that most accurately predicts the desired target value for new data, right? So the measure of model error that is used should be one that achieves this goal. And naturally, any model is highly optimized for the data it was trained on. So the expected error the model exhibits on new data will always be higher than it exhibits on the training data. So you cannot train a model and just report the performance matrix for the training data set. You have to test it on a new data set and report the performance of it. So the figure here illustrates the relationship between the training error and the prediction error for new data. In the middle, this is the optimal of a model. And on the top, you can see the scatter plots. It illustrates the sample data with prediction lines corresponding to different levels of model complexity. So increasing the model complexity will always decrease, right? Will always decrease the error, right? And at very high levels of complexity, we should be able to perfectly predict every single point in the training data set. And the training error should be near 0. So similarly, the true prediction error on new data set, it falls initially, right? As you can see. However, once we pass a certain point, the true prediction error starts to rise. So at these high levels of complexity, the additional complexity we are adding helps us to feed our training data, but it causes the model to do a worse job of predicting on new data. So this phenomenon is called overfitting the training data. So in the overfitting region, the model's training algorithm is focusing on precisely matching random chance variability in the training set that is not presented in the actual population. We can see this model fits every point of the training data. clearly this is too tight a fit to the training data, right? So preventing overfitting is key to building robust and accurate prediction models. Overfitting is very easy to miss when you only looking at the training error. But we can easily find out if the model is overfitted by comparing the training error with the prediction error. If your prediction error is much higher than your training error, that means it is overfitted apparently, right? On the other hand, if your model is too simple, it cannot capture the patterns in the data, or because your training data size is too small, it cannot capture the patterns in the data. So you always get a high level of error when you apply it to both the training and new data set in these cases, right? This is called underfit. So now we have learned this algorithm. We want to apply them to a real world case, which is building performance during hurricane. So in this example, you will be given a data set. It looks like this, right?
Charles, may I interrupt you briefly? Sorry about. There's a question. How can we avoid overfitting?
There are many methods to avoid overfitting. Actually, we will cover this later in our examples, but we can talk some of them now. For example, you want to reduce your model complexity, right, to find the optimal, right? For example, if you are using a random forest or decision tree, you want to reduce the depth of your tree, right? Or you can also do some regularization to your model to throw away some of the features that you have learned. This is used in neural networks. So we will talk about this later in our example. We will talk more about it.
Thank you.
Cool. Not sure if we want to do this example after a break or we do it now.
I think it's a good time for a break. You covered 50 minutes. That's a pretty comprehensive lecture. How about we take a 5-minute break before we go into the lecture, and we reconvene at 10:55 Pacific time.
Okay, cool.